In today's world, future technology and innovation are at the forefront of every conversation, especially when it comes to artificial intelligence, AI. It seems like everyone is discussing AI, but terms like machine learning and deep learning are also part of the mix. How are they related, and how do they differ? Let's break it down in a way that clears up some common misconceptions. Since my last discussion on AI, the field has exploded, especially with the rise of generative AI. Technologies such as large language models and chatbots are now everywhere, and they are quickly reshaping industries. Even technologies like deepfakes fall under this vast AI umbrella. But how do they all connect? In this video, I'll simplify these concepts and help you understand how they work together and where they fit in the world of future tech. To start, AI is essentially about using computers to simulate or surpass human intelligence. This includes the ability to learn, infer, and reason, key characteristics we associate with intelligence. Historically, AI began as a research project, and its early days were mostly theoretical. Artificial intelligence, AI, has evolved from a niche concept to a major focus in the tech world. But this wasn't always the case. The initial idea of AI dates back to the mid-20th century, with the famous Dartmouth Conference of 1956, where computer scientists like John McCarthy first proposed the term artificial intelligence. In its early stages, AI was an academic pursuit, often relegated to university labs where research was mostly theoretical, exploring if machines could mimic human reasoning. This early period saw limited success due to the lack of computational power and large data sets necessary to train intelligent systems. Programming languages like Lisp and Prolog, which were used back then, were the ancestors of modern AI systems. These languages eventually led to the creation of expert systems in the 1980s and 1990s, where computers could make decisions based on predefined rules. This technology laid the foundation for the modern AI we see today. The first wave of AI mainly focused on symbolic AI, sometimes called good old-fashioned AI, where computers were programmed to follow rules and logic. These early AI systems were narrow, limited to tasks like solving mathematical problems or playing chess. By the 1970s and 1980s, interest in AI fluctuated due to the AI winters, periods of reduced funding and optimism as the technology failed to meet overhyped expectations. Machine learning, ML, represents a fundamental shift from early AI. Unlike rule-based systems, ML allows computers to learn from data. This idea was conceptualized as early as the 1950s by Alan Turing, who posed the question, "Can machines think?" He developed the Turing test as a way to measure a machine's ability to exhibit intelligent behavior. However, the key enabler for modern ML came in the 1980s with the development of backpropagation algorithms by scientists like Geoffrey Hinton. This method allowed neural networks to adjust their internal parameters and learn from errors, significantly improving the performance of AI systems. In the 1990s and 2000s, as computational power increased, companies began applying ML in areas like spam detection, fraud prevention, and recommendation algorithms, e.g. Amazon's early success in suggesting products. ML is particularly good at detecting patterns and outliers, data that doesn't fit the usual trend. This is incredibly useful in fields like cybersecurity, where spotting anomalies in user behavior can prevent unauthorized activities. Although machine learning has roots going back several decades, it truly gained momentum in the 2000s and 10s, and is now at the core of many advanced technologies. Deep learning is an advanced subset of machine learning, relying on artificial neural networks inspired by the human brain. Neural networks aren't new. Initial work on them began as far back as the 1940s with the perceptron model by Frank Rosenblatt. But their effectiveness was limited by available technology and the amount of data that could be processed. Deep learning saw a major breakthrough in the 2010s thanks to the availability of big data and graphical processing units, GPUs, which enabled these complex networks to process vast amounts of information. One of the most famous applications of deep learning was Google's AlphaGo, which defeated the world champion at the game of Go in 2016. Unlike traditional ML, deep learning models like convolutional neural networks, CNNs, and recurrent neural networks, RNNs, can handle unstructured data such as images, text, and speech, which led to advancements in fields like natural language processing and computer vision. The explosion of generative AI. Generative AI represents a quantum leap in artificial intelligence. Historically, AI systems were designed to recognize patterns and perform specific tasks, but they didn't create new content. That changed with the development of generative adversarial networks, GANs, by Ian Goodfellow in 2014, which enabled AI to generate realistic images, audio, and video by pitting two neural networks against each other. GANs gave rise to stunning AI-generated artworks and deepfake videos, but also raised ethical concerns. At the core of generative AI are foundation models like large language models, LLMs, which power systems like GPT-3, developed by OpenAI, and BERT, developed by Google. These models are trained on massive data sets and use probabilistic methods to predict and generate text, but they can also create new forms of media. Their impact has been revolutionary, from writing code to creating human-like conversations in chatbots. Foundation models are the underlying structures that enable generative AI to function at its current scale. Unlike traditional AI models that were limited to specific tasks, foundation models are designed to be general-purpose systems. These models are trained on vast amounts of diverse data, everything from books to social media posts, which allows them to understand and generate human-like responses. These models emerged due to advances in transfer learning, a technique where a model trained on one task can be adapted to perform a different task with minimal fine-tuning. The architecture of these models, especially transformer-based models like GPT-3 or T5, enables them to understand context and generate coherent, often complex responses that appear human-like. This marked a dramatic increase in the scale of AI adoption, impacting industries from customer service to healthcare and entertainment. Large language models, LLMs, such as GPT-3, represent one of the most significant advancements in AI. These models don't just autocomplete sentences like a smartphone keyboard. They can generate paragraphs, essays, and even entire stories. LLMs are trained on millions of documents, learning the nuances of language, syntax, and context. Their ability to predict the next word or phrase in a sentence comes from statistical patterns within this data. The underlying architecture of LLMs is based on the transformer model, introduced by Google researchers in 2017. This architecture improved AI's ability to process sequences of data in parallel, making it more efficient for tasks like translation, summarization, and even coding. What sets LLMs apart from previous models is their sheer size and the scale of their training, which allows them to generate more complex and meaningful outputs. Generative AI isn't limited to text. The principles behind large language models have been extended to create AI models that generate audio, video, and even art. For example, OpenAI's DALL-E can generate unique images from textual descriptions, while JukeDeck has pioneered AI-generated music. The creative potential of these systems is enormous, leading to both excitement and ethical concerns. While some argue that generative AI is just recombining existing content, others point out that creativity itself is often a recombination of prior knowledge and experience. AI can now compose symphonies, write screenplays, and even simulate the voices of famous people using deepfake technology.
Would you believe me?
In the entertainment industry, this has led to discussions about copyright and the ethical use of AI-generated content, especially in cases where it's hard to distinguish real from AI-generated works. Deepfakes, powered by generative AI, have become one of the most controversial applications. By using AI to create hyper-realistic videos, audio, or images of people, deepfakes can make it appear as if someone said or did something they never did. While deepfakes have entertainment value, e.g., creating parodies, their potential for misuse, such as spreading disinformation or violating privacy, has led to widespread concern. The technology behind deepfakes relies on neural networks that can analyze thousands of images or voice recordings of a person and then generate entirely new footage that mimics their likeness. This has raised issues around digital identity, security, and trust, as deepfakes can be weaponized in political campaigns, social media, and other platforms to manipulate public opinion. Generative AI brings enormous potential but also significant challenges, particularly around the ethics of content creation. The rise of chatbots and large-scale language models has sparked debates on topics like bias, misinformation, and the rights of content creators. As AI-generated content becomes more sophisticated, it's crucial to develop policies and frameworks that ensure responsible AI use. The rapid rise of generative AI has led governments, corporations, and institutions to rethink how they approach intellectual property, data privacy, and consent. As these technologies continue to evolve, so too will the ethical considerations that come with them. If you enjoyed this breakdown and want to stay ahead of the curve in future technology and innovation, don't forget to like and subscribe. Let me know your thoughts or questions in the comments below.